Well, the last section here, B5, is a real world kinematics example. And this one I thought of when I was preparing this class and led to a publication. My first paper that I guess was published after I retired. Speed, acceleration, and distance plots from a race car speedometer. So looked at a Camaro. Here's a beautiful picture, thanks to Zach Catanzaretti, who let me use it for the publication. A Camaro that was going from 0 to 300 kilometers per hour, a YouTube, it was a stock car practice scenario posted by Harmoudi. And beautiful example, because you can read the speedometer, you can get the data. And when I did that, every second, I was able to get the velocity from the speedometer in that video. And what I wanted to show you in this real world example, in the concepts of calculus, if you recall, when you go from, say, the velocity graph, if you want to go take the slope, you're going to get the acceleration. And if you take the area, you get the x. So that's what I did in this paper, use a real world data where you have your velocities and you have your times, which I converted from kilometers per hour to meters per second to work with, and did this with a spreadsheet. So let's see how you would do the calculation. This is coming from the graph of 2 points. If we look here at 0 time, you have 0 velocity. Then at 1 second, still got 0. At 2 seconds, you got here, velocity comes out to be 0.56 on the meters per second. And at 3 seconds, it's 8.33. So once we have this information, we're going to calculate the slope and then the area. So for the slope, very easy. The slope's rise over run. There is no slope here, so you get 0. And here what we do is we say for the slope at 0 is this one. The slope at 1 is this one, and the slope at 2 is that one. So we're not doing instantaneous information. We're doing like second by second. And the same thing when we do the area. The area from 0 to 1 will be the area value position, say, at 0, which is going to give us 0. And then we're going to calculate the area of a triangle there and the area there. This will tell you how much distance you're going second by second. So after 3 seconds, I just calculate all the area, and that's the position after 3 seconds. So after 0 seconds, or at the beginning of 0, after 1 second, still 0 position, and then here, that position, the area of the triangle, and then the area of the trapezoid, and then you add up the distances to get the total distance. So here, the slope at, say, 2 seconds, let's do this one at 2 seconds, you would go from 0.56 to 8.33, so that's a rise of 7.8, and divide by the run, 1 second. So that's it. That's all you have to do. And that would be the acceleration assigned at 2 seconds, all right, in our model. The acceleration for the 1 second would be the 0.56, subtract 0 and divide by 1, so it's 0.56. So 0.56 and then 7.8, because for the acceleration you got to take this and divide by the 1 second, and that's where the second squared come in. Remember, the units are meters per second squared for the acceleration. So the 7.8 meters per second divided by the 1 second gets you the 7.8 meters per second squared. Now for the area, 0 and 1, the area is 0. So therefore nothing there. And the area here is 1/2 the base, which is 1 second times the height. So 1/2 of 5/6, 0.28. And then the area here would be your area of your trapezoid. You would take here this height, 0.56 and 8.33, and do 1/2 of that, see, and multiply by 1 second. So this is it. So when you work this out, it's around 4. So 4.45 meters, because here your meters per second is going to cancel your seconds. Your meters per second, remember, times seconds is going to leave meters. So that's it. That's it down there. So the distance at 3 seconds would be, well, you would have to add these up. 0, 0, and then you would add, you want the total area at this point. And so when we do that, we get some neat stuff on the spreadsheet. We get this. We had the spreadsheet do it for us, by the way. We don't do it by hand. We just let the spreadsheet do it. And then we get these cool graphs. Here is the velocity as a function of time, straight off the speedometer, all right? And then when you calculate the slopes there, you get the acceleration. Notice it's a little bit jerky at the beginning. Have you ever been on a car that's accelerating from rest and it's a little jerky in the beginning, then it kind of smooths out as you go? You might have some more jerks when you just like switch skiers, for example. And then this is the distance traveled by taking the areas of the velocity graph. And look at that, beautiful. And you could find out here how far the car went. 2,500 meters in 40 seconds. Beautiful example, real world example. And as I say, published, it was in the journal Physics Education. And here's a nice little summary that when you go from this is your X, all right. Remember your D and X sometimes used interchangeably. I like to do the X minus X naught, but if X naught is 0, if you're starting from 0, then X is equal to D. It's the same thing. And then when you take the slope, you get the velocity graph. And when you take the slope of the velocity graph, you get the acceleration graph. And then when you go when you take the area, you're going this way. So integral calculus going to the left and differential calculus going to the right. So that includes our Class B. Hope you enjoyed it. A lot of rich physics in there. We derived the 4 kinematic formulas, and we did a real world example and related to calculus.